This lesson deals with Supplemental Problem 11.1. You can find this problem in the ECE202 ebook in the Chapter 11 Supplemental Problems, starting on page 1. Let's revisit the integrator of Chapter 10. In particular, it was in Supplemental Problem 10.6, which was on page 17, where we looked at the natural response of an integrator and saw that it did not decay to zero as t approached infinity. So by our definition of stability, which was in section 11.1, the integrator is unstable. This is also why the phasor analysis, which was on page 15 of Supplemental Problem 10.6, did not predict the DC level in the simulation on page 16. To better illustrate this, suppose we let the input be a 100 millivolt DC offset. It's worth noting that there are small DC voltage levels present in non-ideal op-amp circuits due to the transistors that are connected to their input terminals. So let's take that splice file from Chapter 10 and let's change our input to being a sine wave with a DC level of 100 millivolts, in other words 0.1. Everything else is the same. Could you run the simulation and plot V out versus time? And then could you calculate V out using the Laplace transform techniques of Chapter 10 and then compare your results with A? So I ran the file and I plotted node voltage 3, and you can see here I have a sinusoidal output, but the output is increasing in magnitude, and as we go more and more with time, our values increase and increase and increase. I stopped it at about 20 volts. Let's do the analysis. In Supplemental Problem 10.6, we had a DC level of 0, and the results that we got with that was this. The answer was minus 3.183 plus 3.183 cosine of 2 pi 1 kt, all times u of t. So we can think of superposition, where we've got the results due to an input with V sub s equal to 0, and now we could find the output due to the input being 100 millivolts. Call that V out double prime. And our transfer function is Z2 over Z1 with a minus sign times V sub s. Z2 was a capacitor of 0.1 microfarads, which is 10 to the minus 7th. So reciprocal of that would be 10 to the 7th divided by S. And then Z1 was a 1K resistor, so it's going to be 1 over 1K, and then times V of S, which is going to be a step with an amplitude of 0.1, so 0.1 divided by S. The S's become an S squared, I have a minus sign, and then I have 10 to the 7th divided by 10 to the 3rd times 10 to the minus 1, and that's 10 to the 3. Taking the inverse Laplace transform of that, from our table in Chapter 9, we have a scalar of minus 10 to the 3, and then 1 over S squared is equal to t, and then I'll multiply by u of t. Then adding our two results, we have minus 3.183 minus 10 to the 3 times t plus 3.183 times the cosine of 2 pi 1k times t, and all of this times u of t. On the simulation above, I marked the value at t equals 20 milliseconds. Let's plug that value into this equation. That minus 3.183 minus 10 to the 3 times 20 milliseconds, and then I have 3.183 times the cosine of 2 pi times 1k times 20 milliseconds. So the k and the milli cancel, and I get 2 pi times 20. So this is a minus 3.183. This is 10 to the 3 and 10 to the minus 3 cancel, so I get a minus 20. Then I have 3.183 times the cosine of 2 pi 20 radians per second. And the value of the cosine is actually equal to 1. So this term cancels with this one. And I get minus 20 volts, which is what I had in the simulation above. And this is Supplemental Problem 11.1.